Chapter 3 was all about how to take derivatives of functions. Chapter 4 is about solving problems using that skill. So key to this chapter is this idea. A function is increasing over an interval if its derivative is positive. Remember, derivative is slope. So if a function slopes uphill, it's increasing and it has a positive derivative. So that's what we can conclude. If a function f of x, it's increasing anywhere that f prime of x is greater than 0. Similarly, a function f of x is decreasing anywhere that f prime of x is less than 0. And just a quick definition, it shows up in your book, it's good to know. Function is monotonic if it's either always increasing or always decreasing. Most of the functions we use are both increasing and decreasing sometimes, but a function is monotonic if it only does one or the other. So we'll do some examples. Can I find all the values of x for which y equals x squared is increasing? Well, this is what we just learned. We want to solve the inequality now. dy dx is greater than 0. That will tell me anywhere that f is increasing because I'm going to find the places where the derivative is positive. The derivative of x squared is 2x, and when I solve this inequality, I could graph it on a number line. It's not required. X is greater than 0 means I'm going to mark 0 here, and I would shade everything over here. And you could have these two choices. You can give your answer here in inequality notation, x is greater than 0, or you could write f of x is increasing on 0 to infinity using interval notation. If you're taking the free response section, you'll have to justify your answer. Your justification would be because f prime of x is greater than 0 on that interval. Similarly, we could figure out where f of x is decreasing by solving the inequality dy dx is less than 0. And you can see that we'll get negative infinity to 0. All values of x that are less than 0. Let's try a more complicated example. So start by fixing your handout. We want to solve this problem instead. So change your function to y equals x cubed plus 3x squared minus 45x. Now, can I figure out where y is increasing? Well, it's going to be any place that dy dx is positive. So I'm going to start by finding the derivative, which is 3x squared plus 6x minus 45. And now I want to solve the inequation dy dx is greater than 0. So I factor out the 3. This is why we've been practicing solving polynomial inequalities. And I'm going to find that there's two x-intercepts for this function. One is at positive 3. One is at positive 3. One is at positive 3. And one is at negative 5. I could try plugging in values from each of these three sections. My recommendation, if you're willing to accept it, is that we make sure we mark this. The sign we care about are the signs of the derivative. I could have labeled that dy dx. So now I'm going to try plugging in values into that same derivative expression. If I plug in a number less than negative 5, it turns out I'll multiply a negative times a negative. The results will be positive. If I plug in 0, I'm going to get 3 times negative 3 times positive 5. The result would be negative. If I plug in numbers bigger than 3, I'm going to get a positive result. And now we can go back to understanding what that polynomial inequality was asking. What values of x make the derivative have a positive result? And we can see here, there's two sections of our number line for which we had positive results. And that's the section from negative infinity through negative 5, and also the section from 3 to infinity. So this is what we would say. Y is increasing on negative infinity to negative 5, union 3 comma infinity, because f prime of x is greater than 0 on that interval. Now it's easy to see what the answer for part B would be. The function y is decreasing anywhere the derivative was negative. Well, we already found out where the derivative was negative. My answer to part B would be on negative 5 to positive 3, because dy dx is negative on that interval.